When developing a property, selecting a driveway material feels like a straightforward line item, but choosing between asphalt and concrete based on the initial quote is one of the most common financial traps in construction. On paper, flexible asphalt presents a highly appealing barrier to entry. For a basic installation, you can expect to pay anywhere from $3 to $7 per square foot. Portland cement concrete, a rigid pavement system, demands a higher upfront investment. Depending on the reinforcement and surface finish, that price ranges from $4 to $15 per square foot. This price differential creates an immediate capital savings of 30 to 50%. These counters show a standard 800 square foot project, where the asphalt quote stops at $2,400, while the concrete total reaches $12,000, incentivizing developers to prioritize short-term cash flow. Prioritizing immediate cash retention introduces a long-term operational liability. It ignores the physical degradation both materials face from the moment they are exposed to the atmosphere. To see why that initial discount disappears, we have to examine the structural mechanics of how these materials distribute weight. Asphalt concrete functions as a multi-layered, flexible structure with low flexural strength. When a vehicle rolls over this cross-section, the load transfers through direct grain-to-grain contact. Red stress vectors push downward in a narrow, concentrated cone. Because the surface flexes, this forces the underlying subgrade soil to absorb the weight, initiating microstructural fatigue. Portland cement concrete operates differently. It functions as a rigid plate resting on an elastic foundation with high flexural strength. Instead of a concentrated cone, it uses beam action. The weight distributes as a broad, shallow wave, bypassing local weaknesses in the soil below. A material's flexural rigidity dictates whether it acts as a structural bridge protecting the earth beneath it, or simply a flexible skin that relies on the soil's stability. Beyond physical weight, extreme weather exposes distinct vulnerabilities in both systems. Asphalt is composed of a petroleum-derived thermoplastic binder, tying its structural integrity directly to the surrounding temperature. A dark asphalt surface has an albedo rating of 0.05. It absorbs up to 95% of incoming solar radiation, driving its internal temperature far above the ambient air. When the outside temperature pushes past 95 degrees, that petroleum binder softens. The pavement loses its shear strength, allowing heavy static loads to leave deep, permanent impressions in the surface. Concrete possesses a high solar reflectance index. By bouncing solar radiation away rather than absorbing it, the rigid slab maintains its structural capacity even in intense summer heat. In freezing climates, that rigidity becomes a liability. Cold weather forces the slab to contract, pulling apart and widening the unsealed control joints between the panels. Any water entering those open joints will expand by 9% upon freezing. This generates destructive hydraulic pressure that fractures the pavement from within, inducing surface spalling. Atmospheric exposure ensures neither surface remains invincible. The specific climate data of your geographic location drives how quickly your pavement will degrade. To survive the elements, asphalt demands a strict, recurring maintenance schedule. The volatile oils in the bitumen continuously oxidize, requiring seal coating every 3 to 5 years to replenish the binder. This schedule is compounded by the routine need for hot pour crack sealing and localized aggregate patching wherever the flexible base gives way. Over a 20-year service life, these operational tasks accumulate to between $2,500 and $6,500 for a typical residential installation. Concrete carries a fraction of that maintenance burden. Upkeep is primarily limited to occasional surface cleaning and replacing the joint sealant roughly once a decade. This chart plots cumulative costs over time. The jagged red maintenance line for asphalt climbs until it intersects the flat blue line of concrete at the year 7 mark. By year 8, the lower maintenance burden of the rigid slab erases asphalt's initial price advantage. Low-cost infrastructure translates a one-time capital expense into an inescapable compounding subscription fee. To evaluate material choices across a multi-decade horizon, civil engineers rely on a mathematical formulation known as lifecycle cost analysis. Calculating the net present value of both systems over a strict 30-year operational period produces figures that appear surprisingly close, roughly $9,100 for asphalt and $9,700 for concrete. At year 30, the physical data shows a divergence. Decades of bitumen oxidation and repeated surface patching leave the asphalt structure too brittle for further repair, necessitating a $6,000 total reconstruction. Meanwhile, the rigid concrete slab retains its flexural capacity for 50 years or more. Beyond the financial ledger, the physical aftermath of dead pavement brings us to the logistics of material circularity and reclaimed aggregate. Despite its ongoing maintenance demands, asphalt is the most heavily recycled material in the United States by mass. The industry reclaims pavement at a 99% rate, offsetting tens of millions of barrels of virgin oil annually. Modern surface engineering evaluates these materials as closed-loop assets, measured over a half-century. The final decision relies on a strict engineering logic matrix. You should select asphalt if your upfront capital is tightly constrained, your site experiences severe freeze-thaw cycles that shatter rigid slabs, or your asset holding period is less than 7 years. Conversely, this decision matrix directs us to concrete for specific parameters. It is the required choice for holding horizons exceeding 15 years, climates routinely pushing past 95 degrees, or properties that must support heavy static loads. Factoring total life cycle economics, rather than reacting to an initial estimate, transforms a pavement system from a constant liability into a stable, durable asset. When procuring infrastructure, optimizing strictly for initial price guarantees a long-term loss. True durability comes from optimizing for the applied physics of your environment.